Now we're going to look at the law of cosines. When do we need the law of cosines? Well, take a look at this triangle, and let's say I try to apply the law of sines to solve for the angles and the side, the missing side. Right? I could say, well, sine of 30 over a is sine of gamma over 12. But that's not super useful here because I've got two unknowns in this equation. I don't know what gamma is, I don't know what a is. And it's not getting any better if I'm using, let's say, beta, because I don't know what beta is either. So, okay, so no matter what pair of expressions I use, I'm always going to get an equality involving two unknowns, and I'm kind of stuck here. So law of sines is not useful here. So we need another law in these cases, especially when you've got an angle and you've got the two sides adjacent to that angle. Okay, so in that case, how do we figure out the missing sides and angles? Okay, so let's take a look at a generic triangle. So we'll come back to that example later on. So consider maybe this triangle, like that. We'll say this is theta. Let's say this is CBA here. Okay. And I'm going to essentially draw an altitude starting from the vertex opposite to theta, okay, and then perpendicular to the extension of side C, like that. And then there's a different case where maybe the triangle looks like that and the altitude is within the triangle. That's also possible. So in either case, okay, I'm going to be able to create somehow a right triangle with an hypotenuse of A. So maybe actually here, let me put A over here. This is C. This is B. And this is still theta. And what I want us to look at is this, this triangle here, or in a right triangle, or in this case, this right triangle. Okay, so what are the sides of this triangle? So let's take a look at that. So to find h, for example, h is what, how do we get h? I can use the fact that sine of theta is opposite. Okay, now I'm looking at this larger triangle here with h, theta, and a. So sine of theta is h over a, so that means that a is, h, sorry, is a sine of theta. Okay, and similarly, this is this part here. Okay, let's call it well, I need to write that it would correspond to this part here. Let's give it another name. Let's say this is x. Okay, then the cosine of theta would be, so this would be x. It would be x over a. So that means x is a cosine theta. Okay. All right. So maybe similarly here, this h here would be also, it would be, oh, did I write? Oh, I made a mistake. This should be b here because it's the hypotenuse. So this is a b here that goes there. Okay, so about that. So this similarly is going to be b sine theta. Okay, So it's again here looking at this triangle with height, right triangle with height h. This could be like x, and this could be b. And again here, the base of the right triangle, so this part here, this is our x. That actually is b cos theta. Okay. Okay, so having this in hand, okay, I can look at the red triangle in each case. So in each case, the red triangle, this one, okay, and it has a hypotenuse of a, and it's the same here. Yeah, look at this one here like that. So the hypotenuse is a. The height in both cases is b sine theta. The base, however, will be different depending on each case. So in this first case, the base is x minus c. So it's going to be b cos theta minus c. And in this case, it's c minus x. So it's c minus b cos of theta. So the only difference is the difference is performed in a different order in each case. Okay. But either way, I've got a right triangle. So I can apply the Pythagorean theorem. So a squared is going to be b sine of theta squared plus b cos theta minus c squared. So this is the Pythagorean theorem. So that's in this case here. But notice that in the other case, I would have c minus b cos theta instead. But when you're going to square this, right? If you do 2 minus 3, let's say squared, or 3 minus 2 squared, you're going to end up the same thing. Because 2 minus 3, 3 minus 2, it has the same absolute value, okay? So when you square it, you're going to get the same number. So in either case, I'm actually going to get this identity, okay? The same Pythagorean identity. So I get a squared is b squared sine squared. So by squaring everything. Here, I'm going to use the fact that this is of the form a minus b squared. So it's going to end up being a squared minus 2ab plus b squared. So I'm going to do that. So I'm squaring, so capital A squared, that's my b cos theta squared, minus 2 times a times b. So I'm going to put actually the c there. So this was written 2bc cos theta plus c squared plus b squared, so which is my capital B. Okay. So I've applied this perfect square formula. Okay. Now I'm going to regroup those two together. Look at that. This is, I can factor b squared, and what I get inside is b sine squared plus cos squared. And you'll remember that this is the same as 1. So overall, my first two terms are just equal to b squared. I'm going to actually put the c squared that I have in the end here, I'm going to put it here, and I've got minus 2bc cos theta that's left. And this identity is called the law of cosines. Okay, so let's apply this to our previous example. So we had, what was it? Like we had, yeah, 10, 12. Okay, so we had a triangle like that, 12, 10. And we were given an angle here of 30 degrees. We want this side, we want those angles. I've called them before beta and gamma. Okay, so what you do first is you calculate A using the law of cosines, because we've got the opposite angle 30 and I've got the angles, the lengths of the sides in between. Okay, so this is pretty important, okay, for the law of cosines, okay, the way we apply it, this theta here, we know the b and the c were actually the values of the sides that were adjacent to the angle, okay. So the a is always a should correspond to the side that's opposite to the angle that's on the right hand side of the law of cosine. So I've got that a squared is 12 squared plus 10 squared. So those are the squares of the adjacent sides to 30 degrees. Minus 2 times b times c times cosine of 30 degrees. And as you can see on this side, I know everything. On the right hand side, I know everything. So a squared is going to be, well, this is 12 squared plus 10 squared minus 240. Cosine of 30 is root 3 over 2. And I can basically calculate this. This is approximately 36.15. And a is just the square root of that. So 6.013. Having calculated a, I could now use the law of sines to calculate the angles, for instance. So I won't do that, but we could calculate beta and gamma using law of cosines. I could also calculate alpha and beta using using the law of sines, so of cosine. So maybe I should. This is kind of an important deal here. So how can we find, let's say, one of the missing angle, gamma? Okay, so for gamma, I could use solution 1. I could use the law of sines now. How so? Well, now I know that sine of 30 degrees divided by its opposite side, which is the side I just found, would be in the same ratio as the sine of gamma over its opposite side, which is 12. Okay, and then I solve for gamma. Okay, solution 2. Solution 2 is also interesting because maybe let's take a look at our triangle again. Okay, this is 12, 12, 10. A was found and it's 6.013, and gamma is unknown. Okay, so now I've got the two sides adjacent to gamma, okay, and the side opposite to gamma. So the side opposite to gamma, in the cosine law of cosines formula, that's kind of like my a. So a squared is equal to the sum of the squares of the two adjacent sides minus 2 times the product of the two adjacent sides times the cosine of gamma. And now I've got an equation involving only gamma, and then we solve for gamma again. So I wrote down quickly the solutions. Look at solution 2. So solution 2, you solve the equation for cos of gamma, and you find that cos of gamma is negative. So that means that gamma is actually an obtuse angle, because if the cosine is negative, we're dealing with an angle so that it ends up with a side that's in the second quadrant. Since the x-coordinate of this point must be negative. So we've got an obtuse angle, gamma, and we find 93.74. The advantage of using cosine here, or the arc cosine eventually to find gamma, is that this angle is always going to be between 0 and pi when we find the, or 0 and 180 when we find the, when you use the arc cosine. Problem with the using the first solution is that we find sine of gamma is 0.997, And it's kind of hard to tell whether gamma is obtuse or acute, because the answer, the way we're going to use arcsine will depend on that, because arcsine is going to give us an angle between 0 and 90 degrees if sine is positive, or 0 and minus 90 degrees and 0 if the sine is negative. That's due to the way the arcsine function is defined. So so very difficult to tell here whether gamma is obtuse or acute. Now we know it's obtuse from the previous answer. So actually here you see that we know that gamma would actually be 180 minus the arcsine of 0.997, and that's going to give us approximately the same answer, 93.74 degrees. So this solution 2 here would be actually preferable, especially in this case because gamma is very close to 90 degrees. Very hard to tell whether it's acute or obtuse.